Well, welcome back. I ran out of time, as seems to be the norm. So this is the completion lecture for my Paxos discussion from this morning. And I am going to take up where I left off. So I was talking about Paxos, and there was a good conversation that we had just started, and then I had to call it, which was about liveness. And one of the interesting observations here was that if you have two different proposers that are sitting there trying to make a change, proposer 1 is doing prepare X, proposer 2 is doing prepare Y, and neither of the proposals gets accepted. And so what happens is that since the previous proposal wasn't accepted, it becomes tabled. And then they should make another proposal. And so you can end up going back and forth with these guys, so they never actually get an accepted proposal. This is a threat to liveness. So Lamport's algorithm in Paxos does not guarantee liveness. I was very upfront about that. If you do not have liveness, then the question becomes, okay, so yeah, how do we make this work in the real world? It's fine in Leslie's world not to have liveness, but how are we going to do this? So what we're going to do is we're going to use some heuristics. So we have a randomized delay in time. We can actually choose a leader. We can actually implement a leader election, and that's in the end what's going to end up happening when we move into view stamp replication slash raft. The trick with these heuristic solutions is that we can't actually defeat FLP, because FLP still applies in the system that we've created. All we've done is decrease the likelihood that we're going to end up in a liveless, a non-live situation where there's lots of messages flowing around, but in fact we're not actually making any progress. This is where the search tests are going to be more difficult in Project 4, because in Project 3, some people did struggle with the search tests. In Project 4, this is a real problem, because we really can have, as you see, we really can have liveness competitions here. And so that search space detection is really going to test this. If you end up with a lot of these kinds of race conditions, and your randomness doesn't actually break enough of them to make forward progress, what's going to happen is you're not going to get very far in the search space, and that test is going to fail. That this isn't something that's imaginary. It's not something we made up for the test. This is actually a real world problem. This kind of behavior comes up over and over again, where we end up implementing some sort of a heuristic solution. So let's look at some other things that we can do with Paxos. And Lamport's original paper does actually lay out Multi-Paxos, which is where, so in single Paxos, we agree on a single value, but in Multi-Paxos, we can agree on an order of multiple values in a particular sequence. So if you think, when we talked about two-phase commit, we talked about having multiple operations within a single transaction. This is logically an extension of that. So the Paxos algorithm we started with is every individual operation is completely independent of every other operation. What happens if we have a series of operations that need to actually be linked together? In multi-Paxos, then what we actually have to do is not only agree on the outcome, but we have to agree on the order of events within that particular sequence. And that's a little more complicated. It does increase the voting that we have to do, increases the number of messages. It does work, and it is a perfectly reasonable way of implementing a much more sophisticated version of Paxos. You're not going to have to do that in Project 4. You just need to be aware that as hard as Project 4 is going to be, you're just working with the simplest of distributed consensus algorithms in terms of Paxos. We're going to start to see more of this as we move into the sharded key value store in Project 5. So you will actually get exposed to this a little bit later. So in Multi-Paxos, we have an optimization where we select a leader for a view. A view now is a sequence of these operations. And when we accept the view, we accept all of the proposals within that particular sequence. And this adds extra state management, because now we have to worry about all of the view, all the changes within a given view. So we roll forward from one view to the next view to the next view. It is similar in some ways to what happens in view stamp replication. and I have links to the ViewStamp replication, the ViewStamp replication revisited paper. You don't have to look at those right now. They are going to come up in the next lecture, because the next lecture is in fact ViewStamp replication and Raft, which are basically the same protocol. They are a similar but different algorithm for coming up with distributed consensus. Paxos is deeply, heavily, frequently used. I mentioned this in class this morning. One of the things that I was kind of surprised as I was reading through Lamport's notes is that both Petal and Frangipani actually used Paxos. These were both, and the links in the slide are to the papers. I'm actually very familiar with Petal and Frangipani. They both are very interesting systems. Petal is a distributed storage system. You remember when we looked at the Corfu work, Petal is much earlier than that. It's not trying to build a distributed log, but Petal is instead trying to build a distributed storage system, a disk level storage system. And then Frangipani implements a distributed file system. And they both actually use Paxos. As far as I can tell, those are the original, actual, real world, as real as a research project can be, real world uses of the Paxos algorithm. They were successful enough that other people have certainly picked up and used Paxos for lots of other projects since then. And I'm mentioning two specific cases here. One is called Chubby. Chubby is a distributed lock manager that is used by Google even today to implement distributed locks. Remember when we were talking about transactions and how we needed to have we had to have transactional locking? Well, a distributed lock manager provides you with a mechanism for implementing transactional locking. And distributed lock managers actually have been around longer than Paxos has been around, for sure. The oldest implementation I know of a distributed lock manager was implemented in VAX VMS. That's a commercial product that Digital Equipment Corporation actually produced sometime in the 80s, I think it is. So a long time ago, 40 plus years ago. Well, almost 40 years ago. It's very important to have consensus in a distributed lock manager because everyone has to agree. There has to be an agreement on who owns a given resource. And when you do distributed lock managers in this kind of a system, you almost always end up using this idea of a timeout. When I was at Stanford, one of the PhD students working with Cheriton at the time actually was working on this kind of time-based locking scheme, what they called leases. And leases are not a new idea today, but they were a pretty interesting idea at the time. And the point was that rather than us giving you unbounded or unfettered control over a resource, the idea was we'd give you a limited control of that resource. It's the same basic problem. Who owns the lease, how long is it good for, and how do we make sure that we have an agreement on who owns that particular lease. If you're familiar with rental real estate in Vancouver, you'll know that sometimes people who don't actually own the property will lease it out to you anyway and keep your money. So we clearly want to avoid those kinds of situations when we move them into our compute centers. Google Chubby, that is a paper that about the Google Distributed Lock Manager. Zookeeper has the Zookeeper Atomic Broadcast, which is a critical, integral part of how Zookeeper itself works. And it is actually a Paxos implementation. So there are two real-world, actually in use projects that are using Paxos. And there are others out there as well. Paxos really did trigger an amazing array of people and working on this distributed consensus algorithm. And we see the original Paxos paper in 1998. Remember, he actually submitted it in 1990. So there was a whole period of time where nobody really knew about this and they weren't really using it. The Petal and Frangipani people used it right after that, 1999 timeframe. And then we see Disk Paxos in 2002 and Cheap Paxos in 2003 and Fast Paxos in 2004 and Generalized Paxos in 2004, 2005, and then we get to Stoppable Paxos in 2008, and I'm not even sure what Minkius is. Then we get to Vertical Paxos, and now we're into 2009. Then we get ePaxos in 2013. There are lots of research papers. There are lots of interesting discussions about this. I actually really liked this animation. Let's see if I can get it to play here. where it's visible. No, it's not going to be visible because, oh, I can move it. I can actually move it down. So here we go. If I can get it on the right screen. Come on, come on, come on. Try to cooperate here. There we go. Thank you. Okay, so you should be able to see that. Let me make sure in OBS Studio. Yeah, you can actually see it. And what's really cool is this actually has an animation of Paxos. And if you just sit there and you watch it, you can actually see the way that you have proposers, and then you get acceptors, and then you get the propagation of things out to the learners. And it's a nice animation, and I like the fact that you sort of sit there and suddenly you see this burst of activity, and that very much is the kind of real world behavior you end up seeing with Paxos. Paxos is typically not used for high volume operations. Paxos is typically used in situations where what you need is strong safety. So for example, if you were building a configuration manager, you might choose to use Paxos because it provides you with the strong safety guarantees so that you know your configuration database is valid. Remember in Project 3, one of the criticisms of Project 3 was, gosh, I have these windows of vulnerability. I have a single point of failure view server. You could replace the view server with a view server that is actually multiple servers implementing a Paxos protocol. And now you have a robust and reliable view server. And this is how we harden our distributed systems. So we get something working, we have our primary backup type of solution, and then we say, okay, now I've got this working, but I have this vulnerable component in the view server. How do I actually fix this so that it's not a vulnerable component anymore? And this helps with that problem. There are other problems in primary backup that we talked about as well. And I'm not saying that you would use Paxos to solve them all, but Paxos is useful in something like a view server where it is in fact very low volume, but very important to the overall performance and behavior correctness of the underlying system. So there you go. That's actually a really nice little animation there. And believe it or not, that's pretty much it. So we're just going to wrap it up here. So what does Paxos give us? It is implementing an asynchronous agreement protocol where we have a basic model of proposers, acceptors, and learners. Now, these roles are separated out, but keep in mind that they might actually be co-resident. If you think of nodes as computers, that's not really the model here. Nodes here are processes. Like if this was a single computer, you might have a process that is a proposer and a process that is an acceptor and a process that is a learner, all on the same computer. So now when you step back and you have multiple computers, because of course that's a fate shared model. Everybody's on the same computer, they're fate sharing. Now when we move across the network, they are no longer fate shared. Now we just have to worry about network communications breakdowns, and we're allowed to have a proposer, an acceptor, and a learner on a single computer system. That works fine. In fact, actually, we could have multiple proposers, multiple acceptors, and multiple learners. One of the things we didn't really talk about, but should hopefully be relatively obvious, is that one of the ways for us to get some scalability out of our Paxos implementation, you remember that whole race condition thing, is if we shard up our decision space. Now, we didn't do that in the original walkthrough, but if we ended up sharding our decision space, you can pretty quickly see how, oh, okay, we can make this stuff all work together. So one learner, one set of proposers, acceptors, and learners is responsible for this piece of the space. This other proposers, acceptors, learners is responsible for this piece of the space. And that way, because as long as there's no collisions between those things, you can reason about it without a problem. It gets harder when you get into Multi-Paxos because now you're modifying multiple things at the same time, and that one is more difficult for you to break up and isolate like that. Still, there are general techniques and mechanisms that you can use for making it very fine-grained and improving performance. Typically, there's a trade-off there. You can make it very fine-grained, but then you use a lot more resources to do that. You get better parallelism. You make it coarse-grained, you use fewer resources, but you get poorer parallelism. For something like a configuration manager, where configurations only change occasionally, you really don't need to do that kind of sharding. For something like a key value store, you probably will need to shard things. And that kind of helps motivate Project 5. We are allowed to lose messages within this environment. Operations can appear out of order. There's no guarantees for ordering. It does not guarantee liveness, and it does not address Byzantine failure. We will talk about Byzantine failure more as the course goes on, but that adds complexity, which we will be able to handle, albeit at a cost. So I just want to get this basic protocol down and to say, look, even with these assumptions about things not being entirely perfect, we can still make this work. It is a widely used and implemented protocol. It's considered even today to be complicated. People often prefer Raft because they find that it's easier to reason about, but there are probably as many implementations of Paxos as there are of Raft. So in Project 4, you are going to build your own Paxos implementation. It doesn't require Project 3, although it does use AMO. A couple of people in the class said, well, but my AMO wasn't very good. I would strongly suggest that you spend some time to make sure that you have a robust AMO implementation. It should not be that large. It should be maybe 5 lines of code, 10 lines of code. It's a very small kind of operation. You feel free to talk to the TAs. They know they should be able to help you work through your own AMO implementation. This is a pretty standard concept. This idea that in order to handle repeating messages, you have to have at most once. In order to guarantee at least once semantics from the clients, you need to have repeating messages. So these two fit together. They solve different problems, and together they give us a nice, strong solution. But you have to be able to implement that. The challenge for AMO is really about Java and the fact that if you have a Java class with a reference to another Java object, then you have to worry about the fact that when you make a new Java object via a copy constructor, that the default constructor that Java provides you is going to copy the reference to that object. So why is that bad? If you change the underlying object, both of the references point to the same object, and therefore they will both see those changes. So if you're trying to store state information to keep track of what happened in the past, you don't want to be looking at something that has been modified out from underneath you because you're going to reach the wrong decisions. That's really what the motivation there is. When you do that, the way that you work around that instead is, instead of saying, okay, I've got this embedded object, I need that has mutable state, because the embedded object really has to have mutable state for this to be interesting. If it's not mutable, it doesn't matter, because it's not going to change. If the embedded object has mutable state, you need to copy the state. So in other words, you need to create a new instance of that object with the preserved state. And that's what makes the deep copy constructor a little more challenging. You can also feel free to ask questions at office hours, or sometimes I find these conversations are better on Discord than they are like even on office hours, because it gives time for people to digest things. I mean, if you force somebody to write things out, it uses a different set of brain cells than if you're talking through things. So I'm going to leave it there. Obviously, the floor is open for questions, but since this is a completion lecture that I'm recording, I expect the questions will come either on Piazza or via Discord. And with that, I'm going to call it a day. You've now seen Paxos. You are through some of the more complicated material in this course. There will be more complicated material, but this is, of all the things that you really will benefit from understanding, is if you can walk out and be able to explain to someone else how Paxos actually works, and be able to answer questions like the ones that came up today in class, which were great questions, by the way, then you're going to find that's very powerful. Because just being able to say, oh yeah, I understand Paxos, and being able to explain it to somebody is actually quite an accomplishment. It's not, as much as I look at it, I go, it's not really that complicated a protocol. It is a complicated protocol. It's complicated because you have to start thinking about oh, what do I do when this goes wrong? What do I do about when this thing happens? So like the race condition between the proposers, or the out of order messages, or the fact that we essentially can have proposals that end up getting dropped on the floor because the proposer abandons them before they get enough votes to commit it. So there we go. I will see everybody on Thursday, and have a great day. Now I just have to figure out how to turn off the recording. All right, bye-bye.